Hello everyone and welcome back to this NPTEL course on aquatic geochemistry. Today we are going to discuss kinetics further. In our last lecture we have been discussing the introduction of kinetics. So, here we stopped and we were trying to find out how we formulate the reaction rate, that is capital R. Okay. So, capital R, if we have a reaction something like this where A plus B produces C plus D, then this is how we are going to write the reaction rate. Okay. The reaction rate is equal to minus of dA. So, you are going to differentiate. Okay. So, differentiate the concentration by the time taken, and whatever is the coefficient here, that will be in the denominator. Okay. So, when you have the reactants, they will be negative. Okay. So, you see the equal to signs here. So, you can write the reaction rate in terms of either the products or the reactants as well. Okay. So, if you are writing in terms of products, then it will be positive. See this is a positive equation, right? There is no negative sign involved in this, right? So, this one, if you are writing this equation, if you are writing in terms of products, it will be positive. If it in terms of reactants, it will be negative. Okay. And other than that, if you are trying to write in a generalized form, so this is the differentiated form, right? Now, if we try to remove this and try to bring in a equal sign, okay, then we are going to add this rate constant term. Okay, we are going to add this rate constant term in the equation, and then we can write equal to, we can give this equal to sign. Okay. And since we are talking about all the solutions, okay, we are talking about aquatic systems. Therefore, what we will do is we will remove all the concentrations and we will use it in terms of activities. Okay. Now, this activity, concentration, juggling of the terms can vary. Okay. If you are not confident of what is the activity, of what can be the what is called the gamma factor, okay, the activity coefficient. If you know the concentration and if you know the activity coefficient, then you can easily calculate activity, right. But if you do not know this, then comes the problem. Okay. So, if you are not sure, you are going to simply assume that your activity is very close to your concentration if it is a diluted solution. If it is a concentrated solution, then that might become a problem. Okay. So, this denotion in terms of activity and concentration depends on how you are going to utilize that. But for solutions, we mostly prefer to use the term activity. And now, what we are going to do is we are going to focus on these terms, okay, N terms, Na, Nb, Nc and Nd. Okay. We are going to focus on these terms. Why we are going to focus on these terms? Because these terms will help us understand how is the rate constant moving, okay, and it will be very evident in our next slide. So, suppose you consider a reaction, okay, and of course, those N terms are called the reaction orders. Okay. This, say suppose you have a reaction where A is just breaking down into some other products. Okay. It can be X, Y, Z, any kind of product. Okay. So, A is having a simple breakdown to form its products. Now, if you are going to try to find out the rate law, how you are going to write? You are going to differentiate the equation with a delta time. Okay. So, you are going to write d concentration of A divided by dt. What is the time difference that you are considering? And that is equal to minus k and a to the power of n. and here n is the order of the equation. Okay, n is the order of the equation that you are trying to find out. So, either you know that or you are going to try to determine that experimentally. So, you are sitting in a lab, you are conducting an experiment and you are going to check how the A value is changing, okay, with time. So, here if you see there is a plot of A, concentration of A, the first plot concentration. So, we are going to see this plot. So, we are having a plot of, in the y axis we have the concentration of A term, okay, the reactant, and on the x axis we have the time term, and we are going to try to see how A is changing with time. Okay. So, if it is a very linear change, so this is very linear change with time, and that is also, if I increase the concentration of A, nothing is happening, it is just following this linear path. So, if I increase the concentration, it is still going to take this, it is still following this, you know, line. So, it is following this linear curve. Then now you check the rate. So, K you plot. Okay. So, this is the rate, okay, that is K, and this is the concentration term. Now, what are we saying here? It is a parallel line to the x axis. When it is a parallel line to the x axis, that means there is no change with the concentration of A, which implies that if I increase my concentration of A, then nothing will happen. Do you understand this, what I am trying to say? I am trying to say that if we change, if we increase the concentration of A, if I go on adding more and more of A, my rate is not changing, nothing is happening to my rate. So, my rate is remaining constant here, it is remaining constant here. That means my reaction is independent of the concentration of A. So, it is not going to change if I go on adding, if I 100 times I multiply the initial concentration and still start the reaction, still the reaction rate will be the same thing. That means it is independent of the concentration of A. Those reactions are called 0th order. Okay. Why 0th order? Because now my n, these are, my n is equal to 0. Okay. It means that my rate is just a constant term. So, minus dA by dt is equal to K, and this remains constant. Okay. There is no change if I add A, that is my reactant. Okay. There is no change in the reaction rate. My reaction does not move any faster if I increase my reactant. So, it is independent of my reactant, particularly A. So, you can have in another complex reaction A plus B plus C, which is going to form, you know, D plus E plus F. And in this kind of reaction, A can remain a 0th order, B and C can be different. Okay. The reaction may be sensitive to B and C and not be sensitive to A. Okay. So, what I mean is that this particular reaction only depends on B and C concentration. If you go on adding B and C, then it will start reacting faster. It does not depend on A, or otherwise it will. So, you can have a variety of reactions. So, those reactions in which a particular reactant does not influence the reaction rate, for them it is the 0th order. only for that reactant it is a 0th order. The entire reaction order is not 0. Only for that reaction, only for that component, only for A it is 0th order. For B and C it might be different. The entire reaction order can be different. What is the entire reaction order? It will be Na plus Nb plus Nc. Okay, that is the reaction order of the entire reaction. That is the total reaction order. Okay. So, you have to find out, if somebody says what is the reaction order of the reaction, then you have to find out in terms of every component and just sum it. If it is 0 for term A, if it is 1 for term B, if it is 2 for term C, then my total reaction order is 3. So, it is a overall reaction order is 3. Okay. So, this is how a 0 order reaction looks like. Okay. When you have a simple A decomposing into a product and that reaction does not depend on the concentration of A, then the overall reaction order is equal to 0, because there is only one reactant, right? Only one reactant is decomposing. So, if you write it in log terms also, the plot will come like this. Okay. So, log of rate, that means this value is giving my log K value and this is my log of concentration. Again, this is a reaction where we do not have any other component. Okay. So, the overall reaction order becomes 0 because A does not have any influence on the reaction rate. Now, let us move on to another kind of reaction where my A is producing B. Okay. So, again A is producing another B. Now, if I plot the concentration of A with time, it is showing a curve. Okay. So, there is some proportionality factor there. Okay. So, there is some proportionality factor coming in. Okay. Now, if I check my rate, if I plot my rate with respect to concentration, I am seeing a linear increase. Okay. I am seeing this as a linear increase. So, my rate is linearly increasing. What does that mean? Now, it means that if I increase my concentration, my reaction rate will also increase. Okay, it is gradually. If my concentration is here, my reaction rate was this value. If I increase my concentration, then my reaction rate value increases. Okay. So, if I increase my concentration, my reaction rate increases. So, this means now that the reaction depends on the concentration of A. If I double the concentration of A, my reaction rate can double. Okay. So, this is the first order reaction, a simple linear increment is going on, a linear increase is going on. Okay. And if you consider the slope, okay, if you take the slope, that will give you K value. Okay. So, you have an angle, okay, and depending on that, how fast it is increasing. If this angle is much if the slope is much shallow, that means the increment is very slow. If the slope is higher, then the increment is much faster, but it is a linear increment. Okay. The unique aspect of first order reactions is it is a linear increment. The rate increases linearly with respect to my reactant. Okay. Now, if you plot it in terms of log, then you will have such a increment, and this is very particular of n equal to 1 reactions. That means, first order reactions. So, this is my first order reaction. Okay. So, for any reaction where the addition of one particular component increases the rate of the reaction linearly, then it is first order reaction with respect to that term, okay, with respect to that phase. Okay. Again, if you are given a complex reaction A plus B plus C equal to D plus E plus F, whereas this is 0 and this is 1 and this is 2, then this means that this reaction, okay, A plus B plus C producing D plus E plus F, the rate of the reaction is linearly increasing with the increasing B concentration. Now, let us move on to the second order reaction. How will a second order reaction look like? Okay. So, if you plot a reaction like this, okay, where you consider again a reaction A is producing B, and now if you plot the concentration of A with time, you see it is exponentially decreasing. There is a exponential decrease. Okay. This is exponentially decreasing. And if you plot the rate term, okay, if you plot the K term, small k, if you plot the K term with the concentration term, you see that it is increasing exponentially. Okay. This is a exponential increase. So, for any reaction, if I increase this concentration, my rate exponentially increases. For those phases, we say that the reaction order with respect to that phase is 2. Okay. This is a second order reaction. This is a second order reaction in terms of this particular phase called A, in terms of that particular component A. So, that means if I increase the concentration a little bit, my reaction rate will increase exponentially. And again, if you plot the log rate with log A value, it will have this linear curve, but here the angle will be much steeper. It will have a very steep angle, and this is the n equal to 2 kind of reactions. So, again if I have A plus B plus C producing D plus E plus F, and my A terms with respect to A it is 0, with respect to B it is 1, and with respect to C it is 2, then the overall reaction order becomes 3. That means, if I increase the A concentration, nothing is going to happen. There will be no change in the formation of D and E and F. If I increase the concentration of B, the reaction rate will be moving linearly. There will be linear increase in the reaction rate if I increase the concentration of B. But if I increase the concentration of C, then my reaction rate will increase exponentially. This is what the physical meaning of reaction orders. Okay, this is how physical meaning of reaction orders, and mostly this is determined in the experiments, and you have to determine this before you fit this in any kind of equation. So, if you are trying to do some kinetic modeling, you are going to do some modeling studies and all, then you have to find out beforehand that what is the reaction order for those particular components. Is the overall reaction order. Now, let us see some other thing. How other than the concentration of the components, what can change the reaction rate? I think all of you know that by heating, that is by increasing the temperature, reaction rates can increase. Okay, I think you can you know this from school days, that if you want to happen, if you want a reaction to happen, then you need to heat it, because heat increases the reaction rate, temperature increases the reaction rates. So, it has been experimentally found that most of the reactions, not all, okay, not all reaction, but most of the reactions are sensitive to temperature, and they can, if you are trying to find out the reaction rate in terms of temperature, then we use this Arrhenius equation, which says that the reaction rate K is equal to A to the power E, which is E to the power minus EA by RT. So, this is a very important reaction. Okay. K is equal to A into E to the power minus EA divided by RT. And if you write in log terms, ln terms, then ln K, because it is E, we are going to write ln and not log. So, in log E terms, that is ln terms, ln K is equal to ln A minus E divided by RT. And what is A? A is called a pre-exponential factor or frequency factor, that if you think of it in physical term, is related to the entropy of the activated complex. Okay, it is related to the entropy of that activated complex, and it is assumed to be a constant that does not vary with temperature. So, it is a constant term not varying with temperature. EA is the activation energy of the reaction, and for every reaction that is determined. Okay. So, it is again a constant and does not vary with temperature. So, for any reaction to happen, the activation energy needs to be fulfilled. Okay. If you fulfill the activation energy, then that remains constant to temperature. And R is the gas constant. Okay. So, if you know the activation energy and if you know the temperature and you know the A term, you can easily find out the change in the reaction rate with increasing temperature, or vice versa. You can, if you are trying to find out what is the activation energy, you can find out. Okay. Now, let us look into the applications of kinetics, and the most important, I think the most relatable and easy, the first thing that you would say is understanding dissolution and growth in an aquatic system. Two opposite terms, one is dissolution, that means there is a compound, there is a salt, something, some mineral that is dissolving in water. Okay. So, that is dissolution reaction. Growth is just the opposite. Growth is something is forming, something is precipitating out of that system. So, dissolution and growth are very, if kinetics controls these kind of reactions. And as I said, that kinetics talks about the path that the reaction is going to take. So, it is important to understand the reaction mechanism. Okay. It depends on the microscopic level changes that is happening in that small system where the reaction is happening, okay, where there is a mineral surface and that is reacting with the water, and it is either dissolving or there is more precipitation happening. And we have found out that generally, this is again generally, there are 5 primary steps to a surface reaction. A surface reaction, that means reaction is happening on this surface. That means this particular mineral is reacting with water and it is dissolving, it is forming some other products, it is getting dissolved, or something is precipitating on the surface with time. Okay. So, surface reactions, there are 5 steps. First, diffusion of the reactants to the surface. So, there is something in the water, there is some dissolved components which has to diffuse and react with the surface, and for that there has to be sorption happening first. Okay. So, not only will, if you have a beaker and you have this particular block of mineral. Okay. So, this is some mineral and that, say suppose it is reacting, it is precipitating out. So, say suppose this is calcium that is precipitating out, calcium carbonate is forming. Okay. So, calcium from that entire system has to find itself, it has to diffuse to that surface. Second step, it has to get sorbed, it has to get sorbed in the surface. Then the reaction has to happen. During the reaction there can be many transition states. Okay, there can be many transition states, and every time a transition state happens, the transition state has to decompose and dissolve. Some components can get dissolved at that time, and again if it is dissolution, whatever the products are forming, that has to go away, diffuse away from the surface again, and the surface has to be clear always, otherwise the reaction will very soon reach saturation, right. Again the surface has to be cleared for continuous reaction, and in theory any one can be the rate controlling step, either the diffusion, either the sorption, either the reaction forming the transition state, or the decomposition of the transition state. Okay. In theory any kind of step can be the rate controlling step, but generally we see that in practical from experiments we have noted that either it is the surface control, okay, the nature of the surface that is interacting, the nature of the surface, or it is a diffusion. Okay. So, diffusion of reactants to a surface and diffusion of reactants away from the surface, that is controlling the rate of the reaction. Okay. For example, so now we are going to see these two types of reactions. So, one is surface control and the other is the diffusion or transport controlled. Okay. So, these two are again we are going to discuss this. So, surface controlled reaction, what do you mean by surface controlled reaction? On the surface, okay, at low degrees of saturation, okay, at low degrees of saturation, it is generally the surface that controls the reaction. Okay, and surface control occurs when the dissolution rate, okay, the dissolution rate is slower than the rate of diffusion. That means, the rate of the dissolution reaction is very slow as compared to the diffusion rate. That means, whenever the product is forming, it is getting time to diffuse out. So, diffusion of the products is not the problem, it is the surface control of the reaction that is causing the slow of the reaction, that is causing the reaction to go slow. And what controls the surface? For instance, if you have a block, so suppose if you have a block of mineral, then you can have different kind of structural defects. Okay. These are the things we call the structural defects. Okay. This is called a step defect. This is called a step defect. Okay. So, what is happening? You have a mineral and then you are going to see this kind of step defect. that means it is broken. So, there is a step, okay. There can be a step, there can be dislocations meaning something which is not supposed to be look, let us say suppose in this particular position you were expecting a sulphate ion, and as compared to a sulphate ion you have found out it is now having a PO4 ion, okay, phosphate ion. Okay, so, that is a dislocation. Okay, so, in terms of one particular element you find something else, or you were expecting a lithium ion, and in that place you find something else. Okay. So, now my lithium is replaced by this X element and lithium is no more available for that reaction. Okay. So, such dislocations can happen in, or you can find a pit, okay. There is a hollow, okay. This place is hollow. So, something it's called a pit. Okay. So, pit, step, kink, okay. Kink means that there is something like this, okay. It is going and it is having a kink like that, okay. So, there is a kink, okay. So, these are the defects, the structural defects. These are the structural defects on the mineral surface, okay. And due to this the reaction can get either faster or slower, okay. Now, during dissolution the atoms with the highest energy, okay, will be the first to react, because they have so much energy, you want to stabilize, you want to lose that energy. So, the highest energy reacts first, okay. And if you have some other kind of sorption, say suppose where the reaction is going to happen at that particular point, you have some other metal, okay. You have some other metal adsorbed onto it, then that particular location is not available for reaction. So, sorbed compounds may poison a surface controlled reactions, okay. It is that particular site is not available for reaction to happen, then that can become a problem, that can slow down the reaction, okay. And surface controlled reactions generally have a higher activation energy than the diffusion controlled reactions, and they are often very high. So, their values are very high in in general it is seen that their values are generally very high in nature, okay. So, these are the surface control reactions, that means it depends on the surface of the mineral, whether there is a kink, whether there is a step, whether there is any dislocation, whether there is any pit, whether there is any other absorbed kind of ions there, okay. So, that controls the surface controlled reactions. Now, let us see diffusion controls reactions. What will happen if the reaction is happening, if the rate at which the reaction is supposed to happen, that is happening faster, but when the products are going, they are very slow. So, all the products they are they are concentrated around the surface, okay. So, they are concentrated around the surface of the reaction and they are not moving again, then this reaction, this diffusion, okay, is very slow, okay. So, you find all the products saturation near the surface, the products are saturating the surface, and the reaction produces only as fast as the excess products can diffuse out. So, all these products has to diffuse out, and it is seen that if you are just going to stir the reaction, if you are just just trying to move away, if you are just trying to move away the products, then the reaction rate increases, okay. Simple reaction, you are trying to dissolve sugar in water. So, what you do? You are just trying to stir the water and the sugar will dissolve faster. So, those are diffusion control reactions, where the reaction rate is very fast and is only dependent on how fast the products are moving away or diffusing away from the reaction surface. And in that case, stirring can speed up the reaction. And these reactions, the diffusion controlled reactions, their activation energy is very low. So, you do not have to heat a lot, okay, as compared to surface controlled reactions whose values can be very high, whose activation energy values can be very, very high. So, with this we come to the end of today's lecture on kinetics. Okay. I have given you certain very basic understanding of thermokinetics, that those things that we commonly apply. Please understand that these can get extremely complicated depending on the nature of the system that you are working with. Okay. And those conditions in which the complexities occur, you need to understand those complexities, and if you try to build a model or something like that, then you have to take those complexities individually. Okay. So, in any system we can have multiple types of complexities. Okay. So, this was just a very basic glance of how thermokinetics can influence aquatic chemistry with very simple reactions such as diffusion, surface controlled reactions, which we definitely know is happening in aquatic systems. But in more complex cases, the complexities will be can be very different. Okay. So, those are very particular cases. With this, I would just suggest that if you want to know more about this, you can look into the treatise on geochemistry book that I suggested in my first lecture, and there is a particular chapter there which is related to modeling at low temperature, and their kinetics has been discussed in very details, and particularly with reference to particular softwares and reaction where you kind of do the reaction calculations in softwares and models. So, if you are going to read that, I think you can understand the application of this, but again it depends on the suitability to your science. If it's required, then please go ahead and you can look up that. With this, I come to an end. In the next lecture, we are going to talk about acids. Thank you.